Welcome back, fellow gearheads. I'm your chief engineer for today, and I am absolutely pumped to get back under the hood with you for another explainer created by Forge College. So, in our last lesson, we walked through the transaction lifecycle. You know, the external logistics of how transactions get ordered. But today, we're grabbing our wrenches and heading straight into the engine room. We are officially bridging the gap from when transactions run to the nitty-gritty reality of how smart contracts actually execute.
All right, let's just quickly glance at our blueprints for today. We're going to cover 1. The execution shift. 2. The great library metaphor. 3. Isolation and determinism. 4. Reading and writing footprints. 5. The token transfer hotspot. And finally, 6. Building for parallel worlds. Let's dive in.
Section 1. The execution shift.
Okay, so let's move from sequencing into the actual runtime engine itself. Now, it's one thing to know the order of operations, right? But how does the runtime actually isolate contract logic? Well, there are 6 concrete steps that are pretty much universal. Whether you're running a single-threaded EVM or a super highly parallel SVM, every contract has to do this. You prepare the context, load the required state, run the actual bytecode, produce the state diffs, validate those results, and then finally commit the changes. But here's the absolute game changer. In a single-threaded serial system, these steps happen in order, one by one, and the diffs are applied immediately. In parallel systems, though, you've got multiple transactions running these exact steps at the exact same time, which means, yeah, the runtime has to wrestle with overlapping diffs and state conflicts. It's wild.
Section 2. The great library metaphor.
To really grasp this without getting totally bogged down in the code, let's just imagine the blockchain state as this massive, kind of chaotic public library. On the left side here, our EVM model is like a single, incredibly strict librarian. Think of like the most unyielding DMV worker you've ever met in your life. They take exactly one request, open exactly one book, write the changes, and completely close it before even looking at the next person in line. It is totally orderly, and absolutely nobody ever fights over a pen. Now on the right side, the SVM model is this wild parallel workflow. The library throws open multiple reading rooms. Dozens of patrons are reading and writing in totally unrelated books at the exact same time. It's incredibly fast, right up until 2 patrons try to write in the exact same book at the exact same millisecond. And that, my friends, requires some serious coordination.
So how do our poor library staff manage all that chaos? Well, there are 3 main mechanisms. First up is the pessimistic lock. This is basically an exclusive lock at the runtime level. If someone is writing in a book, nobody else can even look at it. The developer signal here is super simple. Either avoid shared writes completely, or just accept that your transactions are going to be serialized, and you'll have to wait in line. Second, we have optimistic read and validate. This is speculative execution. The runtime just lets everyone write in a photocopy of the book, and then checks for conflicts at the very end. If there's a mess, it literally throws the copies in the trash and makes you try again. Third, we have declaration and reservation. This is actually what Solana uses. Before you even set foot in the library, you have to explicitly declare a list of the exact books you're going to touch. The runtime looks at everyone's list right there at the door and schedules patrons so they never bump into each other. It is a brilliant system, provided you know exactly what you need up front.
Section 3. Isolation and determinism. Moving out of our library metaphor and back into the strict rules of the runtime, we hit the entire point of a blockchain, the final state. This brings us to the determinism guarantee. Guys, this is the absolute bedrock of a blockchain. It's the ironclad assurance that, given the same ordered set of transactions and inputs, every single honest validator on the network will compute the exact same final state. Now, the single-threaded EVM, it basically gets determinism for free. Since it processes everything sequentially, the state transitions just follow this single, unbroken timeline. But parallel runtimes, oh man, they have to work incredibly hard to pull this off.
See, in parallel systems, scheduling is often non-deterministic. One validator's CPU might process a transaction, say, a microsecond faster than another's. Some of those speculative executions we talked about might get aborted and retried. But the golden rule is absolute, that internal chaos must not affect the final committed state. You absolutely need deterministic commit arbitration. Meaning, even if the journey was this crazy free-for-all across 32 processor cores, the final destination must be mathematically identical across the entire network. No exceptions.
Section 4. Reading and writing footprints.
So how do we actually build for this environment? Well, it all comes down to the code you write. We generally categorize contract code into 4 different footprints. First is pure computation. This requires 0 state writes. None, so it scales perfectly across parallel cores. Second is read-only. Here you're just observing the state without mutating it. This also scales beautifully. But here is where the warning lights start flashing. Third is read, modify, write. You read a piece of shared state, do some math, and write back to that exact same slot. Let me tell you, this is the fastest way to ruin a parallel party because it introduces a massive risk of conflicts. And finally, the cross-account writer. Updating multiple accounts simultaneously drastically complicates the runtime scheduling and recovery efforts. Basically, if your contract relies heavily on those bottom two, you are definitely going to bottleneck the system.
Section 5. The Token Transfer Hotspot.
To really see this bottleneck in action, let's look at a classic disaster scenario we call the token transfer hotspot. Imagine the simultaneous arrival of 3 transactions, A, B, and C. They all hit the network at the exact same millisecond. Transaction A wants to transfer tokens from account X to Y. Transaction B wants to transfer from account X to Z. And transaction C, it wants to read account X's balance, deduct a fee, and write it back. So all 3 are aggressively targeting account X at the exact same time.
Let's see how our 2 different models handle this traffic jam. On the left, we have serial execution. Our calm, orderly librarian simply orders them, A, then B, then C. Transaction A finishes, B looks at the new balance in X, then C looks at the next balance in X. It's a unique, totally safe state transition path. No drama. But on the right, optimistic parallelism. All 3 transactions grab the balance at the same time, do their math, and bam, try to write back all at once. The runtime detects this massive, cartoon-style dust cloud of a collision, has to literally throw all that compute work in the trash and make everyone try again. It's frankly incredibly inefficient.
But if we use a declaration-based system like Solana, we actually save the day, because transactions A, B, and C all had to pre-declare account X as a read-write account. Right at the door, the runtime scheduler immediately spots the overlap. It steps in before execution even begins and either assigns locks or just serializes them for that specific hot slot. So yeah, you sacrifice a tiny bit of parallelism right there on that one account, but you guarantee progress without wasting compute on explosive collisions.
Section 6. Building for parallel worlds. All right, now that we understand the engine, how do we actually survive out there as developers? To avoid race conditions and parallel runtimes, you've got to program defensively. You have to anticipate conflicts. First, prefer idempotent operations. And that just means if an operation accidentally gets retried by the system, it won't break your logic or, double charge a user. Second, use explicit conflict signaling, like compare and swap semantics, to ensure the state hasn't changed underneath you. Third, adopt conservative state access strategies. Only lock what you absolutely need, nothing more. And finally, minimize write contention on shared state. Seriously, stop routing every single transaction through one central status variable if you can avoid it.
As we wrap up, I want to leave you with a provocative thought to chew on. We've seen how runtimes handle isolation and conflicts, right? But how do these isolation choices actually dictate your throughput, latency, and real-world resource costs? Well, we are going to explore the hardcore quantitative answers to those questions in our next explainer on performance trade-offs and runtime constraints. I want to thank you all so much for joining me today. Remember, to dive deeper into this subject and explore a wealth of other awesome Web3 materials, make sure you visit forge.college. Keep building, keep learning, and I will see you in the next explainer.